All right, let's do the solution first, and then we're going to look at another example. Yes, we're going to look at somewhere. In fact, the three occurrence that we have down there is another case. So we can wait until we get there rather than pulling another one into the hat. Okay, now this by itself really doesn't do us much good. Normally, if you want to state how something behaves, how the performance behaves with the input size n, you want something in terms of n, not t of n. So we need to do some more work on this to get that answer. A simple way of solving this is to use what we call a recursion tree. So in a recursion tree, we start by representing different parts of the function with nodes. Now, we can say that for t of n to execute, it's going to end up being broken down in smaller and smaller bits. And we can represent the amount of work done on this tree here. So for t of n to execute, then 3 units of overhead, 3 other units of work will need to be done before you get to the lower core. Agreed, right? So we can say t of n is equal to 3 plus t of n minus 1, right? And similarly for t of n minus 1 to execute, then 3 units of work will need to be done plus t of n minus 2, right? And we can keep on going until each one. The only thing is that we don't know exactly how much n is. We want to make it general. So to get to a general case, we can 3 units of work keep on going down until you reach the general case. So you have a t of n minus k. So if this is level 0, so level 1 is level 2, at when the input size is of n minus k, what do they call that? Level k, right? Now, this will continue down until nk gets equal to n, at which case the input size is 0. So, well, quite often it's drawn. It doesn't have to be drawn, but at this stage, I think, well, board is small. Sometimes you draw one level above level 0, but in this case, because board is small, I won't. So we'll go down until we reach a base case, t of 0, which in this case we know is 1. Right. Now, the important, what we get from this is that we now have a concrete way of working out the amount of work done. In that, once we add up all the overhead across all the levels, we have known the total amount of work required to execute the whole function. So remember, once you execute t of n minus 1, once you execute the recursive call, you really are delaying some work. So once you add up all the overhead, you have now add up all of the delayed work. So now we can then write all of that as a summation from level 0 to level n level n minus 1. At level n minus 1, then you would have been at the case above 5. It may be important to draw the level above. This will be t of n minus k. And this is level n minus 1.
N minus P minus 1.
Sorry, n minus n minus n minus 1. Level n minus 1. So the summation over here is actually the summation from k equals 0 to n minus 1 of 3. And then you add the work done at the base case to get the total amount of work. And that's the work done at base case. Now, to move from k equals 0 to n minus 1, we simply be adding up this number here. How much times are we going to add this number here? Case of variable. This is the actual number that we have to limit. Well, we can give our answer in terms of it. It can remain unknown. But it's just a variable that we can leave in our answer. So the important thing is that we're going to have n different entries from k equals 0 to n minus 1. Alright. If I count from 0 to 9, how many numbers are there? There you go. So if I add this, I know that there are n different numbers. There are n different numbers, and you add 3n times 3 times n. So the answer to this is 3n plus 1. Now, the recursion, well, that's a fairly simple example of recursion tree. The recursion trees can get pretty hairy sometimes. And the second one that we look at might kind of perturb you. But bear in mind, recursion trees are not the only way of solving these relationships. So in the next tutorial, we're going to be looking at the master theorem, which is a simpler way of solving these equations. However, the master theorem doesn't always work in all situations, so it is important to understand how to use recursion trees. So once we look at recursion trees today, it's very likely you may not see them again soon.
Sorry. Alright. Where you have the level n minus 1 on the level 2. Can you clarify that one, please?
We're going to keep on breaking down the recursion until we get to the base case. Now, the case above the base case is the last case in which you're going to have another call. So the argument to this would have to be 1. So n minus n minus 1 is actually 1. So this is actually t of 1.
Okay. Because it would be the same thing as saying n minus 0.
Well, what the level below that will have n being 0.
N minus 1 would be, so you're going to n minus 3.
But the point I think to take away from this is that to find the total amount of work, Add up the work done in the recursive calls and then add the work at the base case. That's the point.